Okay, welcome back here. Quick video time. We're going to talk about ways to classify reactions or types of reactions. And really, the focus of this quick video is going to be redox reactions. If I could get that E to work there. There it is. Redox reactions. So we're going to talk about redox reactions here. There is really two big types of reactions, kind of big classification of reactions that pretty much all reactions fall under, and that is redox reactions, and the other is double displacement reactions, which we will probably tackle in another video here. So we're going to talk mainly in this one about redox reactions. Again, stay tuned. Another quick video on double displacement might be coming down the pipe. But let's take a look at redox. So what does redox mean? Redox is oxidation and reduction reactions. And basically, for all reactions, there's really kind of like three reasons a reaction takes place. You could almost classify or find one of these three reasons for all reactions. The three reasons are a solid is formed, which is sometimes referred to as a precipitate, PPT. You made our favorite thing, H2O, a little bit of water, are really the focus of redox reactions. There was some type of transfer of electrons. So pretty much all reactions boil down to one of these three things occurring: solid being formed, making water, and a transfer of electrons. Precipitation, water formation, those are really in your double displacement reactions. Transfer of electrons, that's all about redox. So let's talk a little bit about redox. There are a couple definitions of oxidation and reduction. So basically, oxidation means that something has lost an electron or will lose an electron. Reduction means that you gain an electron. Now, in organic chemistry, they talk about oxidation as something that gains oxygen as you go from reactants to products, or loses hydrogen as you go from reactants to products. And reduction is basically the opposite, is something that loses oxygen as you go from reactants to products, or gains hydrogen as you go from reactants to products. We're not going to really get into the organic definitions. We're just going to stick with the losing and gaining of electrons here. And it's really important to understand that these two things always occur together. So it's always happening together. So if something's being oxidized, something else is being reduced. When you lose electrons, you actually become more positive. When you gain electrons, you actually become more negative. Now, what's the deal with this? Well, the deal with this is you could actually figure out, in most cases, what is being oxidized and what is being reduced by what is really known as the oxidation state that's going on, or oxidation number, for an element on the left-hand side and the right-hand side. If your class doesn't really talk about oxidation states or numbers, you can think of it more like a charge. It is a little bit different, but you could kind of think of it like a charge. What the charge is when the thing starts on the left-hand side of the arrow to what it ends with on the right-hand side. So you can figure out by using actually just a basic number line situation, where on a number line, there's positive numbers to the right of 0 and negative numbers to the left. If you lose electrons, you're going to become more positive, which means if you find yourself moving in this direction on the number line, as you look at the oxidation state or charge on the left-hand side of the arrow to the right-hand side of the arrow, that thing is going through oxidation. Now, if you gain electrons and being reduced, you would be moving on this way on the number line towards the negative numbers, and that thing would be going through reduction. Now, sometimes people remember this with the oil rig. Oxidizing is losing, reducing is gaining. Some people are fond of the classic Leo the lion goes grr, and loss of electrons, oxidation, gaining of electrons, reduction. Heck, put Leo the lion on the oil rig, he'll go grr. You don't have to choose, you could just put them all together and you basically figure it out. So how does this work in practice? Well, let's take a look at a reaction here. Let's take a sodium metal and react it with a little bit of chlorine gas and make a little sodium chloride over here. And since we just talked about balancing in a previous video, I'll put a link up there in case you didn't miss it, or you did miss it and want to see it again. We'll balance this up like good chemistry students here. Now, when we look at what's going on here in terms of their oxidation state, or again, if you just want to think about it as their charge, when you have any element from the periodic table that's not combined with anybody else, how it naturally comes just by itself, they have no charge, or a zero oxidation state basically. So this would actually be 0 for the sodium. This would actually be 0 for the chlorine, because that is naturally how it comes. When those two guys get together, our metal and non-metal, that's when we start to get charges, and we have an ionic compound. And the sodium here is group 1, which means it has a +1 charge. The chloride's group 7, has a -1 charge. So if we're looking to see what's going on, if we just take our little number line here and positive, negative, we take our sodium, starts right about there. It is 0 on the left-hand side, ends up at +1 here on the right-hand side, becomes more positive, which means it is being oxidized and going through oxidation. One of the nice things about oxidation reduction is if you could successfully identify one thing, what's happening with that one, by default, this guy is getting reduced or going through reduction. And they always occur together. So if somebody gets oxidized, somebody gets reduced. We could even do it for chlorine though. We started with chlorine right here at 0, and it ends at -1. Going to the negative side is being reduced in this case. So this is a redox reaction that's occurring. What is actually happening here is our metal is sending some electrons over to our non-metal that's accepting them. And thus, one of the reasons why a reaction takes place, a transfer of electrons are basically happening here. So that's oxidation and reduction reactions. And you can identify it based on what's happening. Even if you have two metals, for example. By the way, when we have a metal and a non-metal, this is always what should happen, because that's how you make an ionic compound. And again, if you didn't see that video about ionic bonding, I'll put a link up here for you to watch it. But a metal basically will always transfer electrons to the non-metal. So when you always have a metal and non-metal together and you're trying to decide who's being oxidized, it should be the metal, and the non-metal should be gaining the electrons and being reduced. But if you had, say, a metal on both sides of the arrow, let's just go with +2, iron with a +2 charge to iron with a +3 charge. So the oxidation state of these ions are what the charges are. So that's +2 for this guy and +3. So again, if I go to my number line here, my iron is starting at +2, which is here. And it's actually ending at +3, which is moving in this direction more positive, which means in this case, my iron here is actually being oxidized. So again, the number line works well for whatever, as long as you can figure out what the oxidation state or the charge is on each side. You just draw an arrow. If it points to the positive side, becoming oxidized. If it points to the negative side, becoming reduced. So redox are these type of reactions that involve transfer of electrons. We're not going to go super deep into the redox reactions because the purpose of this video is to classify reactions. but we just want to get an idea of what a redox reaction is. So once again, a redox reaction is the big umbrella for which we can have more specific classifications of reactions. So one more specific classification is what is known as a synthesis reaction. And that's sometimes referred to as a combination reaction. And in a synthesis or combination reaction, basically we take two things and we make one thing. Yeah. So for example, if we take some magnesium plus some oxygen, make a little magnesium oxide. Again, chemistry class, we'll do a little balancing action here, 2 and a 2. This is your classic synthesis reaction or combination. The one we just saw as well, our sodium plus our chlorine, making our sodium chloride in this case. Again, a little balancing action here. So once again, if we look at it, two things make one thing, two things make one thing, classic synthesis or combination. So this is a synthesis or combination reaction. And if you can't guess by now, it is still a redox reaction. So we obviously did this guy a second ago. We look at this one, magnesium here by itself, 0. Oxygen by itself, 0. When the magnesium oxygen get together, a little ionic compound happening, +2, group 2, -2, group 6. So once again, if we lay up our number line here, plus and minus, we take a look at magnesium starting at 0, ending at +2, definitely moving in the positive direction. That means here again, our magnesium is being oxidized. Looking at the oxygen, starting at 0 and ending at -2, becoming more negative, it is being reduced. So a more specific classification for these reactions are synthesis or combination reactions, but they are ultimately still, as you can see, a redox reaction happening. Same idea, we are sending electrons over in this particular case. So again, a transfer of electrons. Another classification reaction is really the opposite of that one, which is a decomposition. In a decomposition reaction, by the way, still a redox reaction, we're going to take one thing and break it apart into two or more things. So basically, if we run some electrical current over water, we will break apart water into hydrogen gas and a little bit of oxygen gas. Just need like a 9-volt battery and a little bit of water. You can do it correctly, do it safely, don't do it at home. We will basically do a 2 there and a 2 there, and I think almost at that point. So this is obviously here, one thing makes two things. So one thing makes two things, a decomposition reaction. We could also see something like, if I can find the pen again, a little bicarbonate or carbonic acid, I'm sorry. A little carbonic acid will break apart into water and a little CO2 action. Again, one thing makes two things. This is still a redox reaction that's happening here. By the way, decomposition, as you can also see, is really the opposite of a synthesis reaction. In a synthesis reaction, we take two things, make one thing, put it together. Decomposition, we basically break it apart. So they're kind of opposites of each other. The oxygen here in water actually has a -2 charge. The hydrogen actually has a +1 charge. On the right-hand side, hydrogen is how it naturally comes, no charge. Oxygen, how it naturally comes, no charge. Once again, if we look at our handy dandy number line here, hydrogen is starting at +1, maybe about here, and ending on the right-hand side in this reaction at 0, moving in the negative direction. It is the hydrogen here that is being reduced. Oxygen is starting at -2 over here and ending at 0, moving in the positive direction. And it is the oxygen here that is being oxidized. So again, even though this is probably most of the time classified as a decomposition reaction, we have still electrons being transferred, and it is still under the big umbrella of a redox reaction. So we have single replacement reactions is our next sort of classification. So single replacement reactions. Sometimes people call it single displacement reactions or single exchange reactions. In this reaction, we have a simple setup of A plus BC. And what we know about this is this could be a metal, and this is an ionic compound, which is a positive negative thing. Now, this metal has no charge to begin with, but when it comes in, it will actually kick out the positive guy because it will then make a positive charge when it does that and make a new ionic compound. And that guy that it comes in and kicks out will actually come out by itself and have no charge. So for example, if we take a little magnesium plus some hydrochloric acid, this is your classic single replacement. This is a metal, no charge or oxidation state. This is hydrochloric acid plus 1 minus 1. The magnesium will come in and kick out the hydrogen. When it does, that is when the magnesium will gain a charge and make magnesium chloride in this case. And the hydrogen will come out by itself in its natural form, which is hydrogen gas. I know, a little balancing because we are in chemistry lecture here. So do a little balancing there. So let's see what's happening in this case. Well, this magnesium now has a +2 charge, chloride's -1, and hydrogen is 0. So who's being oxidized, who's being reduced? Because I feel like it should be happening, and it is. So let's take a look. Little number line action. Nice sound effect. Magnesium starting at 0 on the left and ending at +2, which means it's moving in the positive direction. Maybe no surprise here, magnesium is being oxidized. When we look over here, it is actually the hydrogen that's doing something. The hydrogen is starting at +1 and ending at 0 on the right hand side. It's becoming more negative. The hydrogen here is actually being reduced. Now you might be asking, what's going on with the chloride? Well, chloride's -1 on the left, -1 on the right. Nothing's happening with the chloride. It is what is known as a spectator ion, really. It's just kind of hanging out and watching what's going on. It's not really changing at all. So what's really happening here is the magnesium is actually sending its electrons to the hydrogen. And the hydrogen is picking up those electrons and now becoming hydrogen gas. You'll see some bubbles, and you'll see our magnesium chloride really floating around the solution as ions, basically. So this is a single replacement reaction. It is also still, as you can see, a redox reaction as well. Now, you can do this same setup with actually an ionic compound, and this could be a non-metal too, by the way. And in this case, what will happen is the non-metal has no charge. It will come in and kick out the negative guy if it's a non-metal. It will form a new ionic compound, and the guy that it gets kicked out will come out with no charge. So if we take something like chlorine and react it with sodium bromide, chlorine, no charge, how temperature comes, +1, -1, ionic compound. Chlorine going to come in and kick out the bromine here, and will make sodium chloride. And the bromine will come out in its natural form over here. Again, a little bit of balancing as well. Again, on the right-hand side, now that sodium +1, chloride -1, and this guy is 0. How it naturally comes. So this is a single replacement reaction involving a non-metal exchange. I know you probably could guess, still redox reaction happening here. We take a look at the chlorine on the left is 0. chlorine on the right is -1, it is moving in this direction, making it more negative, which means it is the chlorine being reduced. The sodium here is +1 here, +1 here. Actually, nothing happening with the sodium. It's actually the bromine here that's changing. The bromide goes from -1, and on the right hand side it ends up at 0, which means it's moving in the positive direction, and the bromide is actually being oxidized in this case. So again, single replacement reaction, still a redox reaction happening, but we have basically this one guy coming in and kicking somebody out. Now, will this reaction always occur? Well, the answer is no, it will not always occur. So when we look at something like this, say that's a metal, whatever it may be, whatever is coming in needs to be more reactive than what it is replacing. And if it is not more reactive than what it is replacing, the reaction will not take place. So for example, if you tried that copper with hydrochloric acid reaction, you will actually get no reaction. And that is because copper is less reactive than hydrogen. So when it tries to come in here and kick out the hydrogen, it will not do it. There is something known as an activity series of elements, and usually a basic one, you have hydrogen kind of in the middle, a bunch of elements on top, and a bunch of elements on the bottom. And anybody higher in the list will replace anybody lower in the list. Anybody lower in the list will not replace anybody higher in the list. So for example, if you look at this list, you see magnesium higher than hydrogen, so that reaction will take place. But you'll see copper lower than hydrogen on the list, and that reaction will not take place. By the way, the one we did with the non-metals, that's our friends from group 7 on the periodic table, where we have fluorine, chlorine, bromine, and iodide. That is the activity series for the halogens. Going up in the group is more reactive. So fluorine will replace chlorine, chlorine will replace bromine, bromine will replace iodine, and vice versa. Any of those guys, basically. Iodine pretty much will not be able to replace anybody because it's lower on the list than everybody. So again, group 7 is its own activity series. Reactivity increases as you go up group 7. And again, anything higher in group 7 will replace somebody lower. Anybody lower in group 7 will not replace anybody higher. One last sort of classification of reaction is a combustion reaction. And combustion reaction is also a redox reaction. And most people, when they talk about combustion reaction, talk about a organic combustion reaction. In organic combustion, you have some type of carbon, hydrogen, oxygen type of compound, plus some O2 makes CO2 plus water. So if you take methane, like you're going to light a Bunsen burner, plus some oxygen, makes a little CO2 plus some water here. And again, we could do a little balancing, like good chemistry students. You take propane. Makes a little CO2 plus water. So usually if you have an organic guy, oxygen on the left, CO2 plus water on the right is made. Unless you have an incomplete combustion, you'll get a carbon monoxide instead of carbon dioxide. I know we should balance it. So we'll go 3, we'll go 4, we'll go 5, and now we're balanced. Now, another definition of combustion is essentially all you need for something to be a combustion reaction is the presence of O2. So the presence of O2 will make something a combustion reaction. And that means if you had something like this guy that we saw earlier, and a little 2 there, I think. This technically can be a combustion reaction. It's got oxygen. Now I know what you're saying to yourself. wasn't this also a synthesis reaction? Because we got two things that make one thing. You're right. So it's combustion reaction is a synthesis reaction. Let's go for the trifecta here. It's also a redox reaction like we talked about as well. So this one reaction can actually be classified 3 different ways, which is very common for reaction classifications. The way you should classify it is sort of what you're looking at, trying to take the best sort of classification. I would say most people probably would go synthesis for this reaction or combustion, but it definitely is still a redox reaction. So you can definitely classify a reaction in multiple ways. And the way you want to do it is just whichever way is best sort of classification for what you're looking at. All right, we're going to wrap this quick one up here for these types of classifications, which are redox reactions. Again, redox reactions, big umbrella. Underneath that umbrella, we got synthesis reaction. We have decomposition, single replacement, combustion reaction as more specific ways of classifying a redox reaction. I hope this helped, and we'll see you on the next one, probably about double displacement reactions, which will cover the other 2 reasons why a reaction takes place. Anything else you want to know about, just let me know. Otherwise, we'll see you on the next one. Thanks for watching. Bye-bye.